In this video, we're going to start investigating some of what we call Newton's laws of motion. Isaac Newton is a big name in physics. I'm sure you've all heard of him. But he developed three particular laws of motion. He did a lot of things, like develop calculus. But one of his main contributions are the three laws of motion that bear his name. There's other laws, like the universal law of gravitation, which we'll study later. But we're going to start looking at his three laws of motion. And so the first one, to illustrate what the first one says and what it means, I just looked around my office where I'm making this video, and I grabbed some everyday object. It's a little knick-knack off of my desk. I don't know, it used to be my dad's. I always liked it. I took it at some point. It's just this little thing with it's got an hourglass and a deconstructed watch. I think it's supposed to be ironic. Whatever, I always liked it as a kid, so now it sits on my desk. But it doesn't matter what object, and you can do this at your home, wherever you're watching this. Just look at an object around you and ask yourself, what is that object actually doing, right? What is it doing right now? In the case of this thing, not much. Actually, it is sitting still, as long as I don't hit it, which I did a few times, still on my desk, right? Actually, that's what this thing is actually doing. You can say that that's its state of motion, although that's a little bit unclear. That's not a rigorously defined term, but it's actually sitting still. Now, imagine, if you will, what it could potentially be doing. In other words, are there certain states of motion that this is not undergoing, but that potentially it could be? Let's see if we can list a few. Potentially, right? And notice the language here. We've got actually, we've got potentially. Potentially, it could, we don't have to number these. This is not going to be an exhaustive list, but just what the heck. It could slide across the desk, right? Another thing that it could potentially do is fall off the desk. Another thing it could potentially do is spin, right? It could go round and round. And the list can go on and on and on and on and on. There is a whole, almost an infinite set of potential states of motion. There also is a large set of states that are not available to this. It could potentially never turn into a chicken and start clucking and walking around my office. That would be cool, and I hope I catch it on video if it does happen. But realistically, that is not a potential that is available to this object. These are available to it. It could slide across the desk, it could fall off of the desk, it could spin. Now, what it's actually sitting here, potentially doing any one of these things. So the question is, how do I move this object from what it's actually doing to what it could potentially be doing? And the answer is that I have to come in from the outside of this object and make it do one of those things, right? The older language, the Aristotelian language here, is that an action is something that actualizes a potential, right? I take one of these potential states of motion and I turn it into the actual state of motion of this thing. And in that case, what it's actually doing right now would slide down to the potential list, right? It could potentially be sitting still on my desk, but right now it's actually sliding across the desk, or whichever one it's doing. So an action is necessary. Notice an action has to come from outside. I can sit here till the end of time, and it's not going to do any one of these things as long as nobody comes in and touches it or blows on it, or there's no earthquakes or anything like that. All of those actions, those things which could actualize one of these potentials, come from the outside. For instance, let's actualize the first potential, right? I think I actually actualized several of them, right? I made it slide across the desk. Maybe I can do it here, right? It slid. that potential state of motion became its actual state of motion. How did it do that? I came in from the outside and I performed an action, which the older literal meaning of that word is that I actualized one of these potentials. Let's actualize the third one. Right? That was kind of cool. Let's do it again. How did I do that? Did I just wish for it to happen? Did I ask it nicely? Did I yell at it? Did I just think about it? No, I came in and performed an action. I touched it. I exerted, to use the more modern language, I exerted a force. Now, when you see the word action in physics, you should take that to be logically equivalent to what we've been calling a force. This is the older language. I like it. It still sticks around a lot. We talk about later. We're going to talk about potential energy, right, which comes from this word. But the action and potential are all connected. But for the more modern usage, we're going to probably use the word force more than the word action. But I want you to see that logically they are equivalent. Now, that's important, because when I say force, you probably think of something, coming in and hitting something, which of course is part of what happens. But what you're actually doing when you apply a force is you are taking something's actual state of motion and changing it, right? You are actualizing one of its potential states and letting its current actual state become potential. Okay, that's enough philosophy for one day. Let me give you then Newton's first law of motion, which puts all of this together. In the absence of a net external force, an object will not accelerate. In the absence of a net external force, an object will not accelerate. Let's match up some of these words with what we've been talking about. First, accelerate. What is an acceleration? It's a change in the velocity of an object. Well, if the object has a velocity at all, then its position is going to change. This by definition of what a velocity is. So if I change the velocity, I necessarily change something about the position. I could cause it to sit still, but it would be a change from what it was doing, right? The acceleration here is what mathematically relates what we know of to this idea of a potential state of motion. I accelerate it, thereby that takes one of these potentials to an actuality. So what this says, in the absence of a net external force, an object will not do that. This is what we said. If I don't come in and actualize one of these potentials, they never get actualized. The actual state of motion just keeps on happening forever. That's what this is saying. Another important word is external. There are lots of actions. There are lots of forces occurring within this thing. Every atom or molecule in there is exerting forces on the others around it. But its state of motion is not changing. Those forces are internal to the system, and they cannot change the state of motion of the entire system. Just like you can't pick yourself up off of the ground by grabbing your belt and yanking upwards as hard as you can. Please feel free to try it. We would all appreciate videos of that. But you can't do it. You will never get off the ground just by pulling on your belt. You can do other things like bend your legs and jump. But in that case, there is an external force being applied to you. It comes from the ground. But just grabbing your belt and pulling up will never get you off the ground, because that is a force internal to your system. It could break your belt, because you can consider that force to be external to the belt. But if your system is you and everything on you, that force is never going to get you off the ground. So external is very important. Net is also very important. What does net mean? It means I'm going to add some things together. Right? Forces are vectors. We know that vectors add together. So this does not say in the absence of any force, an object will not accelerate. This says in the absence of a net external force. There could be tons of forces acting on this object right now. But as long as they sum up to 0, that means there's no net external force, the object will not accelerate. In fact, if you've watched the free body diagram video, you know that there are forces acting on this right now. There's a support force from the table that's acting up towards the camera. There's a force of gravity acting downwards. The fact that they're in opposite directions might give you some inclination as to see how that they're going to cancel, right? And that might tell you that, give you some inclination to understand that they are equal and opposite forces, equal in magnitude, opposite in direction, right? But they're going to cancel out, and there's no net external force. Does not mean there are no forces. It just means they all add up to 0. This is Newton's first law in a nutshell. You find it stated other ways. This is my favorite way to say it. You can also form the converse of this. In the presence of a net external force, an object will accelerate. Both of those statements are true. Both of them are acceptable ways to talk about Newton's second law. I tend to prefer this one, or not second law, sorry, first law. I tend to prefer this one, but either way works for me. As long as you understand what it's saying, that is good enough for me. That is Newton's first law of motion. In the absence of a net external force, an object will not accelerate.